Hello everyone. We will talk about some principles of point estimation and how do we evaluate the estimation. So before we start, let's learn about certain terms that we will be using more often. So let's start with a population that has some parameter. It could be proportion of success, or it could be mu, the average of certain outcome, gain, age, income, or a standard deviation. So we call these parameters, and that will be here. Now we are interested in estimating the value of these parameters. So usually we will take a sample, then we will use the data in this sample to estimate these parameters, and we may come with p hat, mu hat, or sigma hat, the estimate. Now these, we call them statistic that represent the parameters that we don't know their values. Now, how did we get to the value of these statistic? We probably use certain algorithm or mechanism to estimate and come with specific values for p hat, mu hat, sigma hat. This algorithm, we call it point estimator. Why point? Because you are assigning a single value to each one of them. So that is a point. And the algorithm itself, we call it an estimator. And after we figure out a certain value, for example, we come up with proportion 0.28 or mu, the average salary 70,000. Now these values here, we call them point estimate. So these are parameters. These are statistic. The algorithm that assign value to this statistic, we call it point estimator. And when we assign an actual value to each of these p hat, mu hat, or statistic, we call it point estimate. And why point? Because it's a single value. Now the question is, if we come up with an estimator, an algorithm to estimate certain parameter, how do we know? How do we test it? How do we decide, oh, this is a good algorithm to estimate a parameter? So that's something we have to come up with a measure to this estimator. The second is, what method or technique do we use to come up with this algorithm, to come up with this estimator? That's the second question we have to answer in this section. And before we start, let's agree on the following. The parameters here that we call sometimes mu, sometimes proportion, sometimes standard deviation, we will assign it theta to denote the unknown parameter. And after we estimate, then we will call it theta hat to denote an estimator of theta. Now the first question, how do we determine if the estimate is good or not? We use accuracy and precision, similar to what we did in chapter 3 when we evaluate error. So just imagine you come up with an algorithm to estimate average. So you have a population here, another population here, a third population here, and you are trying to estimate mu1 for this population, mu2 for this population, mu3 for this population. So you come up with your algorithm or point estimator, and let's just assume the actual value for mu1 is here, the actual value for mu2 is here, the actual value for mu3 is here. And you used your point estimator and you estimated mu1 to be this value here, mu2 to be this value here, mu3 to be this value here. So this is mu hat, mu2 hat, mu3 hat. Then we say your estimator is not accurate because it's always overestimated the value. It's always estimate a larger value here. So it's not accurate. You are overestimating. Some other estimator may be underestimating. So that's what we mean by accuracy. Now precision, an estimator or an algorithm you came up with, sometimes it estimated here the value for mu1, sometimes it estimates for mu2 here, another time maybe here for mu3. Same algorithm, but you apply it for different population, and these are the estimate. Versus another point estimator, maybe it estimates sometimes here, sometimes here, sometimes here. For this one and this one, the estimate for this one and this one. Definitely the algorithm that is represented by the orange has a poor precision because the difference is huge. Sometimes more by little, sometimes less by a lot, sometimes more by more than the actual value. Then we say it's not precise like the green estimator. And that's what we mean by a measure of the goodness of an estimator. We use accuracy and precision, and these two things are combined in something we call mean square error. So let's define what's the mean square error. It's very simple. The error here, the E here stands for the following. You take the difference between the actual value and the estimate. The difference will be the error. Then you square it. So then you square it here. Then you take the mean of the square error, because you're going to be using your algorithm, as we said, maybe for 3 different populations. Same algorithm, and you are trying to estimate theta 1, theta 2, theta 3. And you estimate these by theta 1 hat, theta 2 hat, theta 3 hat. So you used your point estimator and you came up with these values. Now I want to measure the goodness of it. So I will take the difference between theta 1, the actual value, and theta 1 hat, and the difference here too, and the difference here too. And then I will square each one of them and I will get a value. So then I add these plus these, then I divide by 3 because I have 3 data points, and that will be the mean square error. And that is a measure widely used in estimating a signal. For example, you may have an image and you have these pixels in the image of value. Sometimes you send the image, it get corrupted, then you have to estimate the corrupted pixels. Somebody else come up with another algorithm to estimate the pixels, and you want to see which algorithm is better. So you apply the mean square error. That means you find the difference between the actual image that was transmitted and the image received after you do error correction. That means estimation of corrupted pixels. And you find the mean square error for both algorithm, and you decide which one is better. And that could be also a voice transmitted. And sometimes it could be just a compression algorithm. So you have this image, there we have JPEG, we have TIFF compression. So you compress this image, and then from the compressed data, you reconstruct the image again, and you want to compare the two images, the compressed image to the original. By compression, you reduce the amount of data you need to store and transmit, but you're going to lose some quality. So we want to know how much difference between the original and the compressed image. Sometimes they use the mean square error to decide is JPEG better or TIFF better or another different algorithm. So you're going to be seeing mean square error in many applications, but it's the same way you calculate for probability or compression or error recovery and estimation. So that's what is the mean square error. But when you run the calculation, you can use it this way, that's fine, or you can use it this way, the mean square error. You find the mean of the estimated value, that means you find the mean of this value and this value and this value. You add them up, divide by 3, you find the mean, which is this, minus the actual value of the data. In this case, it could be theta 1 plus theta 2 plus theta 3 divided by 3. And the difference will be the error, then you square it, plus the variation in your estimate in this one. How much variation between theta 1, theta 2, theta 3. So you use this method, or this equation is the same. It's easier to use this one. And to prove that both of them are the same is very simple. We can prove it. Let's erase this. Okay, so we are trying to prove these are the same. So we will do the following. Mu theta hat minus theta square equal the integral of theta hat minus theta square, the density function theta hat d. Now, this is the same as theta hat square minus 2 theta hat theta plus theta square f theta hat d. And this equal f theta hat d theta hat minus integral Now this one is mu theta hat square, that's this one, minus theta is a fixed value, so with the 2 can come out. Now the integral of theta hat with that density function will give you mu theta hat, plus theta square will come out of the integral, and the integral of the density function is just 1. Now mu theta hat square, I can subtract here mu theta hat square, but I have to add the same amount if I'm going to subtract. So then I have mu theta hat square. So this is just 0. You add the same amount, you subtract the same amount. Minus this comes here, 2 theta plus theta square. Now this quantity here is just the variance of theta hat. And this will be plus mu square theta hat minus 2 theta plus theta square. And finally, this is theta hat. This one here, I can write it as mu theta hat minus theta square. And this is exactly the same as this. So we just showed you can calculate the mean square error this way, or you can calculate the mean square error this way, and both are correct. And the mean square error is a measure of how good is the estimate. It shows you accuracy, the difference between the estimate and the actual value, and precision, how much variation in the estimate. Now in real life, you will have a lot of data. So when I want to test a point estimator, I will take this algorithm, will give it many data, different value of theta for different operation, and I will use the point estimator to come up with theta hat. So maybe here I have 100 data point, and here I will have 100 data point for theta hat. And if the point estimator is excellent, then this 100 data point will be exactly the same. Then the mean square error will be 0. But in real life, this 100 data point will be different than the actual 100. And then I calculate the mean square error using this 100 data point just by carrying out this simple operation. And I will get a value. The smaller the mean square error, the better my point estimator or the algorithm. And sometimes this mean square error is a statistical measure. Sometimes I will look at the image and they will look excellent, but the mean square error said it's poor quality. So in certain application, you need human judgment, but mean square error is widely used. Okay, let's do this example. So we have a random variable x. It has a binomial distribution with np, where p is unknown. So I have a population here. I took a sample of size n, and I don't know p, the parameter. So I need to come up with an estimator. So somebody told us, oh, the estimator, that's very simple. You just count how many success you have here, and that will be your x. And your estimate, p, will be just this one, x over n. X is the number of success, n is the total data in the samples. Now I want to know how good is this estimate. So I'm going to calculate the mean square error. If I want to calculate the mean square error, first I need to find this mu. I need to find this variance. So for this example, mu hat, that means I need to find mu p hat. The variance theta hat, that means I need to find the variance p hat. And that is the parameter I'm trying to estimate is just the p. So let's find first the mean. So from here, same as we did in chapter 3, mu p hat is 1 over n is a constant, mu x. And x, the sample here came from this population. So the average of this population is the average mu of binomial distribution, which is np. And we show that when we study the binomial distribution. And n will cancel, and that is p. So if I calculate the accuracy, it is the mean of p hat, which is p, minus theta, which is p. That's 0. So this point estimate is very accurate, but we still have to look at the precision component of the mean square error. So now if I calculate the precision, that means I need to find the variance of p hat. So that will be here, 1 over n is a constant, so that will be 1 over n squared times the variance of x. That is 1 over n squared. X is a random variable with binomial distribution. So the variance of x, we found it in chapter 3, is just np1 minus p. So n will cancel one of n here, and you have p1 minus p over n, and that's the variance. So the mean square error then for this point estimator algorithm equal the accuracy here, which we found it to be 0, plus the variance, this one, which we found it to be p1 minus p over n. That's how good is this estimator. Now, the next question is, how do we come up with an estimator? For this one, it is very obvious. How do you estimate the proportion? It's just the number of success divided by the total. But other parameter more complex that you want to estimate, how do we come with a point estimator? What method do we follow to come up with a good estimator? Well, this is the topic of here, the method of maximum likelihood. So we come up with an estimator of a parameter that will maximize the likelihood function, which we will define what is the likelihood function. Here, when a probability mass function for a discrete random variable or probability density function for a continuous random variable considered to be a function of the parameter we are trying to estimate, then we call this function likelihood function. So all the probability mass function we learned for a discrete, like this one, np px times 1 minus p, that's for the binomial, that's a function, but it's a probability mass function. And the parameter we are trying to estimate could be the proportion p. Then this, we call it likelihood function. Or for the exponential density function, lambda e minus lambda x. Now the parameter we are trying to estimate is lambda, and this is the probability density function. So now f of x, I can consider it as a likelihood function. Now the maximum likelihood estimate is the value of the parameter of this, the value of the estimate for the parameter we are trying to estimate, or in this case, the value of the estimate here, p hat. Here it will be lambda hat, to estimate the parameter such that it make the data more predicted. For example, if I estimated lambda, then I ask you what's the probability that the waiting time will be between 10 seconds and 20 seconds. If I carry out the integral of these from 10 to 20, then this will give me a very good prediction. So we have to maximize the likelihood estimate. And let's take an example to show what we mean by that. So let's look at this example. X is a binomial distribution with n is 20. So I conducted the 20 trial or 20 experiment. And I have the parameter p that I don't know, the proportion of success. So I don't know the p. Suppose we observe the value x7. So I conducted the experiment, and I found success 7. Then find the maximum likelihood estimate of p. So to solve this problem, first express the probability mass function. So that it will be 7, the number of success, and I will put p here because I don't know the value of it. So since this is a binomial, then the probability mass function will be n factorial divided by x factorial, which is 7, n minus x, that's 13 factorial, time p, the probability of success that I don't know and I am trying to estimate, time 1 minus p, the probability of failure. 20 minus 7, that's 13 failure. So now all I did is I found the likelihood function. So now I have to maximize this likelihood function using the p parameter, the proportion. So how do I maximize these with respect to p? So I'm gonna choose a value for p that will maximize this function. So if I conduct the experiment again and I carried out 30, n equal 30, then if I use that p, it can predict accurately the number of success in the sample. That means it will predict accurately x. So to maximize these, we just take the derivative of f with respect to the parameter p and set that to 0 and solve for p. Before we do that, let's take the natural log for both because it will simplify the derivative. So if I take the natural log of f This will be natural log of 20 factorial minus the natural log of 7 factorial minus the natural log of 13 factorial plus natural log of P7 plus natural log of 1 minus P13. Let's simplify this more. So this is natural log of f. This will be the same constant. Plus this 7 will be here. 7 natural log of p plus 13 natural log of 1 minus p. And now let's take the derivative with respect to p, partial derivative. So this is a constant, the derivative 0 minus a constant, derivative 0 minus a constant, the derivative 0 plus 7. The derivative with respect to p, that will be 1 over p. The derivative of this one, that will be 13 over 1 minus p times the derivative inside the parentheses. So that's minus 1. And this set it to equal 0 and then solve for p to maximize this quantity. So you will get 7 over p equal 13 over 1 minus p. Then do the cross product. So you have 7 minus 7p equal 13p. And finally, it will be 7 equal 20p. And from here, p equals 7 over 20. And that's the estimate. So I should have put here hat to indicate this is the estimate for the probability here in the population. We used the maximum likelihood approach. So we came up with the likelihood function, which in this case, the mass function. If it's continuous, it will be the density function. And then I estimate this by taking the derivative with respect to lambda, and we set it to 0. Now, the desirable property in the maximum likelihood is 2. In most cases, as the sample size n increase, the bias of the maximum likelihood estimator converges to 0. And also, when we increase n, the variance of the maximum likelihood estimator converge to a theoretical minimum value. So the larger the sample, the better idea you will have, the better is your estimate. It will have 0 bias and you will minimize the variation, which is the precision, which is this one. Okay, I will stop here, and in the next video, we will talk about the probability plots. Thank you for watching and see you in the next video.